Hi. Today's video is going to be dealing with another way to, another technique of integration. And we're going to start with this one, x squared times natural log of x dx, and learn a way to evaluate this integral. So if you look at this one, we are going to use something called integration by parts in order to evaluate integrals, and that's our objective. In order to do this technique of integration, we're going to have it in this form. U, the antiderivative of u dv, and the formula is equal to u times v minus the antiderivative v du. Important thing to note here is that this method is particularly useful for integrands involving the product of algebraic and transcendental functions. Also included in there are trigonometric functions as well, you will see as part of today's little video. Comes from the product rule, integration by parts. So if you look at this, here's the derivative of a product, uv, and the product rule for derivatives is uv prime plus u prime v. And what I'm going to do is, we know that the integral of this side would be equal to the integral of both of these components. So that's what we have right here. And by now moving this around a little bit, you will see that we have the antiderivative uv prime dx equal to uv minus the antiderivative u prime v dx, and that is integration by parts. So we need to get our integrals into this form in order to apply this rule. Let's look back at our original problem. The guidelines for finding integration by parts, and here is our original problem that we had, and what we're going to need to do is, down here, we're going to have to select a dv, and that dv is the most complicated portion of the integrand that fits a basic integration rule. And the reason why that is when we pick that dv, remember it has to be in that u dv form, we're going to have to take the antiderivative of it. So if we were to pick natural log of x for that dv, well, again, does it fit our basic integration law? So then the next part we are going to have to do is pick a u. And that u needs to be the portion of the integrand whose derivative is simpler than the function u. So if we go back up here, look, if I were to take the antiderivative of this x squared, we would end up with x to the third over 3 as my v. And if I were to take the derivative of my u, it is going to become simpler than the function u, because that, as we know, is 1 over x. So again, the important part is picking this u and this dv so it fits the form for integration by parts, and then finding v and du. Now we're going to actually apply that rule of integration by parts now that we have all of our things. So this slide is extremely important as you practice and do this integration technique. So again, in order to fit that technique here, we have our u dv, which we saw, our u, which was natural log of x. Here is our u, and this x squared dx is our dv. So it fits in that form. So then our formula, uv, so our u, natural log of x, times v. Remember, we took the integral of x squared in order to get x to the third over 3 minus our v, which is x squared, and then our du, which is the derivative of natural log of x, which is 1 over x dx. So that's how we apply the formula. Now we're hoping that by using this integration technique, or by setting this all up, this integrand here is now something that we can do, and you will see that that is true. I rewrite the first part of it, and now if you look at it using some simplification, we get the antiderivative of x, which is really equal to the natural log of x times x cubed over 3 minus x squared over 2 plus c. So that is the antiderivative, or the integral, of our x squared natural log of x. Let's move on. Here's another example. Again, we have an algebraic function x multiplied by a trigonometric function cosine x. So we have to fit it in this form, u dv. So that means we have to select. Now, if you remember our guidelines of what we're going to pick, you might think right now, what is going to be our u? What is going to be our dv? If you selected your dv to be cosine x, you would be correct. Now taking the integral of dv, I'm sorry, there should be a dx right here as well. We have sine x. So our u is going to be our x. Now when we take the derivative of our u, it becomes simpler. It becomes 1 dx. Now we're going to apply the formula. So again, we have our u dv equal to uv, so there's our u, there's our v, minus the integrand of sine x dx. Now again, we're hoping that this right here is something that we can take the integral that fits one of those basic integral rules. And in this case, it does. And that is our answer. So again, this part up here is going to be the, I won't say most difficult part, but you know, it relies on that, and we'll see some examples in class where we select the wrong u in dv and what happens in that case. But let's move on. Yes, you might have to take a double take. This is very similar to the one previous, but we have an x squared cosine x instead of just an x cosine x. We have to get it in that form now. Again, take a moment and see if you can pick. Now you might think, well, we just did one just like this, so it's probably going to be very similar. And in fact, you are correct. Our dv, again, I forgot my dx here, taking that antiderivative of that to get the sine x. And then now our u is x squared, and our du would be 2x dx. Now let's fit it into this form. Alright, we did that. We got it in the formula. Our uv minus our antiderivative v du. Now our goal again is to have this be something that we can take the integral using one of the basic integration rules. Well, getting it like this, what do you notice? Do we know x sine x? The answer is no. We don't know that. That doesn't fit one of our basic integration rules. So you might be thinking at this point, what are we going to do? Some of you may already realize that we are going to have to do integration by parts again for x sine x. So you're going to have to go through the same process. Pick a dv, pick a u, find your v, find your du. So take a couple of minutes, pause the video, see if you can come up with that on your own. And if you do, and you do it correctly, you should arrive at this correct answer down here. So again, a little introduction to an integration technique known as integration by parts. What you're going to do in your homework is practice that, especially picking. You'll see in the homework it progresses you through. First, it gives you the u and dv, and then from there, then you're going to have to select on your own. You may see different, just to kind of finish up, you may see dv as v prime as well. You may see this. Like in your textbook, I believe they don't do v, they do v prime. And you may see du again as u prime. As calculus BC students, though, I would assume that you would be able to make that connection. All right. Well, I hope you enjoyed this video on integration by parts. Try it in your homework and be prepared in class to discuss integration by parts and applying it. John Stone, out.